Okay, thank you for coming for this 13 week. So without further ado, I want to share the content of our class today. So our content for our class today is more on the wall modeling by using finite element software. Okay, so this modeling is very useful for some of the project that you have with you now will deal with the modeling of wall or slab. So in order to do that, we have to use certain element so that we can model the behavior of the wall appropriately. So before we start, we have to know the learning outcome or the lesson outcome. So the learning outcome we started to know on how to model the slab element or the wall element by using shell. So this is a new element that you learn today by using shell. Okay, and this shell has a special properties that will be discussed after this. And under shell element, we have a lot of element types. So you have to use what is the proper element types in order to have a good accuracy of your modeling. And also you have to decide what is the mesh number that you should choose in for your created model. So the model you created is the wall model. And the member sections such as the thickness, and also its material properties such as the Young modulus, the Poisson ratio, and maybe you have density. You can incorporate it in the model, and each of the element should be subjected to loadings. And in our case, we are referring to static loadings only, and will be have certain boundary condition. Maybe it can fix, it can be pin, it can be roller, and so on. And by using the finite element solver, the solver that you will use is CCX. So what is CCX? CCX is the Calculix software. Calculix solver that is responsible to analyze the structure by using McQuay. So we run the static analysis using that solver. And after you get the analysis done, we able to view the behavior of the deformed shape of that wall. And also we can also study how the internal forces will be distributed along the wall dimension. And also maybe we want to study other parameters such as strain and so on. Okay, so those are the lesson outcome that you want to cover today. And I will talk now the problem itself. Okay, so this is the problem that is given to you. Is a wall, but the wall is placed lie on certain surface. So this is our wall with certain thickness of 0.05 meter. The thickness of the wall is about 50 millimeter. And the length of the wall is 8 meter by 1 meter. And the material properties that made the wall is a Young modulus, and it is a linear elastic material with the value of 1 exponent 10 to the power of 7 kilopascal. This is the Young modulus, and the Poisson ratio is 0.25. It is noted that the edges AD, okay, so if I draw this in 3D, so this part will be fixed, is fixed. So when I say fixed, meaning that the translational movement in X, Y, and Z, so we have three kind of movements here, will be constraints all to be 0 meter, meaning that it cannot translate in any directions. and also cannot rotate. The rotations also in X, Y, and Z axis also to be 0 radian. Because we want to specify this all to be fixed. And in order to simulate the twisting or torsion that acting on the wall, so we subject one of the node here with a point load of 1 kilonewton downwards, and there is 1 kilonewton also acting upwards that is acting at node C at the bottom here. So this effect will create a twisting or torsion. So maybe you still remember torsion. You still remember study torsion in your laboratory CES 511 and your solid mechanic CES 41204121. So hopefully you still remember this, and we want to study this by using finite element software. So on modeling approach, so we have to plan how to model it, because there is one complication. So what are the complications? We want to model the twisting. So how to model twisting so that the structure can twist or being you have which is under torsion force. So if you use plate element that you have learned before, if you still remember your plane stress last week. So if you use this plane stress to model this, it is not sufficient. Why? Because this plane stress cannot take care the twisting problem. So therefore, in order to solve that problem, we have to use a special element called as shell element. Shell element has the capability to have out of plane displacement. This is the benefit of using shell element. So by simulating out of plane displacement, you're able to model torsion. You're able to model torsion sufficiently, and you can view what is the behavior of the wall when it's subjected to that kind of loads. Okay, that is the modeling part. Analysis part, we have to use 3D static analysis, and it is subjected to CCX solver. CCX stands for Calculix. This is the name of the solver that has been developed by programmer to assist us to analyze the wall. So as usual, to model the structure, we have to create what are the nodes and what are the coordinates that you should insert to the McQuaid. Remember, this is your wall. Okay, this is the wall. So for modeling part, we have to model only the middle part of the wall. We model only the middle part of the wall. Okay, where the length of the wall is 8 meters in this direction, and let's say this is in X direction, and it will be 1 meter in this direction. Let's say my Y axis to be in this sense, and in the thickness direction, this is a 0.05. I don't know why my marker doesn't have any mark. Okay, and this is your Z direction. So never mind, I will change my pen a bit. Okay. Okay, now I can use this 0.05 meter. Okay, so as I said, we model only the middle part. So when we model by using McQuaid, we just model only the mid part only. And you have to establish 4 nodes. Okay, where this is maybe nodes number 1, 2, 3, and 4. And as I said, this is our x-axis, this is our y-axis, and the top, the perpendicular, that is a Z, and this is your 0, 0. Okay, nodes number 2 to be 8, 0 logically because the distance is 8 meters. Nodes number 3 to be 8, 1, and nodes number 4 to be 0.1. Okay, so you just model the middle part of the structures only. Okay, and that will be our approach to solve the problem. Okay, so after you create the elements of the coordinates, then you have to select the element type. As usual, for shell element, you have two kind of elements. The first one is the quadrilateral element. Quadrilateral element, which is like this. Okay, and also you have a triangular element. Triangular elements. Okay, and let's say in this case I'm using quad 4. Quad 4 meaning that you have a rectangular element here with 4 nodes, and each of the nodes will have 2 degrees of freedom, which is able to move horizontally and able to move vertically. So you have that degrees of freedom for each of the nodes. And to make our analysis to be much better, we will assume that the displacement from one node to the next node is varied by quadratic. So meaning that the variation of the displacement is assumed to be in the quadratic function like this. Similarly, also like this, you assume the displacement will be in the quadratic, and quadratic. Why you choose quadratic? Because it is performing much better than a linear element. So when I said linear element, so please let me rub this. I don't know why I cannot rub this. Okay. So if let's say you choose a linear element, linear element meaning that you assume the variation of displacement will be in linear fashion, like this, linear fashion. So by using linear, you are not able to capture the non-linearities of the geometry, so that it cannot perform better than the quadratic. Because quadratic much more flexible. It is more flexible to capture the non-linearities properties. Okay, so to make your model to be much more better, we have to perform divisions along the horizontal axis and also the vertical axis. So this meaning that if let's say you have defined the element, then you have to know how many division in the in the horizontal. So in this case, I will use 24. So here I will divide this into 24 divisions. And for vertical, I will use 24. So vertical will be divided into 4 divisions. 1, 2, 3, 4. And T is only defined if you model for 3D case. Remember, this is only 2D case. And if you still remember my drawing, we are only drawing or modeling the middle part of the wall, which is this as 2D, bukan 3D. It's a 2D. That's why we cannot do anything on this T. So we just said it's only 1. So far, is there any questions?
Tak ada, sir. Okay.
Okay. So this is how will the model will looks when you mesh by 24 and 4, as given here. You will mesh it. You will mesh the given element to be in the sense of number of meshing. Okay. So as usual, as I said, we will use this quad 4. Quad 4. So I will use quad 4 where you have 4 nodes, and each of the node can will have 2 degrees of freedom. This is the first degree of freedom, second degree of freedom. Okay, and then we have to put the shell. Sorry, I have to put the shell element with a thickness of 0.05 meter. Remember that our thickness of the shell is, mana gambar dia? 0.05 the thickness. Okay. Okay. And we have to define also the material properties. So the material properties is an isotropic material with a Young modulus of 1 exponent 7 kilopascal. So this is not right. This is not Pascal. This is kilopascal, and the Poisson ratio is 0.25. The Poisson ratio is 0.25, and the Young modulus to be 1 exponent 7 kilopascal. And we still remember that our the shell element, we know that this part to be fixed. So that's why I will select all of the nodes here to be fixed. Fixed meaning that there is no translation movement. The translation movement, which is X, Y, and Z, all are 0 meter, cannot move. And there is no also rotation at X, Y, and Z, which is 0 radian. So it cannot translate, it cannot move because it is fixed. And the last part is to model the your load, the twisting load, which is acting here. So that's why I will create a load here, a point load, which is acting in the Z direction. Remember, this is your X, this is your Y, and this is in your Z. So I will establish 1 kilonewton here in the positive direction of Z, and another force here which is acting in the reverse direction of Z with the magnitude of 1 kilonewton. So by using this, you will create a torsion on this wall, and you want to study the behavior of the wall once it is under the twisting loads. Any questions so far?
No, sir.
So the 2-point loads that created on the node is to create the twisting effect or the torsion effect. This is after we run using the CCX solver. After using CCX solver, then you can view what is the displacement behavior. And if you still remember, we applied the load in the Z direction. So logically, we have to investigate the deflection in the Z direction lah. You apply in the Z direction, so must be deflected in the Z direction. So by viewing that in the Z direction, the maximum displacement was found to be 23.2 exponent 3 meter. You can see that from the diagram. From the diagram, you may see that it is 23.2 there, okay, which is in the color of red here. And also we have negative 23.2 exponent 3, which is with the color of blue here. So meaning that this will be displaced to this direction, and this one will be displaced in that direction, because positive and negative. So to see whether our model is correct or not, this before doing that, we have to see that this is the deformed shape. You may see that the part is being torsion. There is torque applied, so you may see that it is being rotated. Being rotated. Okay, to view whether our model is correct or not, we can compare the simulation with other software, and I will use Abacus software, and it is taken from that website. So for 8 meters, remember that our plate or our shell is 8 meter in distance. This is 8 meter in distance. So by plugging the value to the graph, so this graph is invented by Abacus. So by using this 8, I can draw a straight line vertically, and you can see that the results of the displacement is varying from 21 until 26 times 10 to the power of -3. However, by using our macro software, and we have already used 24 times 4 meshing scheme, our displacement is found to be 23.2 exponent -3 meter, which lies inside this range, meaning that our model is to be okay because the value that you obtain from the software is within the range. Yeah? So we can see that our model by using 24 and 4 is correct. Yeah? Why? Because from by comparing with other software, the result is within the acceptable range. Okay? Is there any questions? Ada soalan persoalan?
No, sir.
No, sir.
Okay, those are the results about the displacement. Now I want to view the stresses results, and I want to know the shear stress results. So by taking axis XY, remember that this is stress in XY. You may see that the wall will have a tension force here with the color of red, with the magnitude of 1414 Pascal. Pascal maksudnya Newton per meter squared. And if we see the drawing, yang ni saya tak rotate, nanti kita akan tengok nanti. If we see the wall from the other side, then you may see that the wall experiencing compression force due to the shear stress. And we can also view the bending stress if you want. You may see that the bending is always maximum somewhere at the location of your fix, whereas it's very, very minimal here. Because green here meaning that it is a very low here, almost zero. But red here meaning that 546, and blue color here meaning that is a compression. So you have compression force even though you applied the load in this sense. You ada kat sini, tetapi dekat sini tak ada banyak sangat stresses. And you can also view the strain lah kalau you nak tengok strain and so on. So we want to do some demonstration by using MacWay using the same model. So I will open my MacWay. Okay, as usual, we have to create our nodes. So 00 is created here. 80, you can see that this is the second points. 81, so I'm modeling the middle part of your wall. This is 81, and the last node is 01. Okay, view it from XY axis and make it to be zoom. And if I want to see the nodes number, I can do that by clicking this button. You can see the nodes number. Okay, next is to define the element. So click this new element. I will select my quad 4, and I will choose that 4 nodes so that it can connect it, and you have defined already the shell element. Okay, so click this button to select the element itself. Right click the mouse and click on the mesh tools and click refine and the custom. Change this as we have agreed. This is to be 24 by 4, and once I click apply, you may see that the horizontal is being divided into 24, and the vertical direction will be divided into 4 equal divisions. So maybe I want to view this in isometric view. Okay, and let's say we define the material properties. So select this, right click, assign new materials, use the shell element with the thickness of 0.05, And the mechanical properties, change this to be kilopascal. This is 1 exponent 7, 0.25, and click OK. Now I want to assign this part to be fixed. So activate the nodes, select the required nodes, click loads and constraint the new displacement, ensure you click x-axis to be 0, so meaning that there is no displacement in x. Repeat the same approach, new displacement in y-axis to be 0 also. Do the similarly with z. Again, also do for the rotation, new node rotation in x to be 0, new node rotation in y also to be 0, and the last one, new node rotation in z also to be 0. Okay. Okay, next is to define the load. So I will click this point and then right click new force. So that is acting in z direction in kilonewton, 1 kilonewton. So maybe it should be reverse. So we just double click this and change this to be -1. Once I click OK, it will reverse. And repeat the same process. This will be kilonewton, and this will be 1. Okay, so we can save this model, save as, and we name it as wall. Okay, run the so before you run, you may want to see the thickness. You can click this show thickness. Sorry, this part. You can view that the wall have its own thickness. If I rotate this, the thickness of the wall from this point to this point is 50 mm. So, okay, we run this. Okay, hopefully, okay, before doing that, I did not remember. Click this analysis, change to be CCX, calculix. Rerun it again. You can see the detail if you want, click the details. And you can see what is the description about our model. You have 6,269 nodes to be analyzed. Elements, you have 96. And then you have a lot of equations. So the number of simultaneous linear equations is about 1,589. It's a quite large number. Okay. So now I want to view the displacement. So in Z, you can see that the displacement is 23.13. Okay, here, and negative 23.13 at the top. So if you view the deformed shape, I can click this one, and you may see that it is being deformed by torsion mode. Okay, if I rotate, you can see that. Sorry. If I perform rotation, you may see that it is being twisted. There is twisting force creating these kind of deformations. Okay, and let's see if I want to view the animation. I can click this animation. You may see that the wall is being is under torsion force. Okay, and you can rotate this if you want. You can rotate to view how it's being deformed. Okay, so I want to stop this animation. And if let's say you want to view the stresses, you can click the stress. So XY is the shear force, shear stress. As I said before, the shear stress is tensile here. But if I flip this wall, you can see that on the other side, it is compression. So you have both tension and compression on two sides of the wall. So meaning that the wall is experiencing couple stresses. Okay, so if you want to view the bending stress, we can make this one Okay, sorry, I have to make it in isometric. Okay, this is our bending stress. Okay, the bending stress. If you want to zoom, you can zoom. Okay, you may see that the stresses is maximum here, the bending stress. This is maximum in tension, which is about 1.6. Kita boleh tukar unit kalau tak suka Pascal, kita buat megapascal. 1.609 megapascal here in tension, and 1.609 here megapascal in compression. And it is being gradually decreases from 1.6 now to be 1.25, and then being reduced to 0.8, being reduced to 0.178, and so on. Okay, is there any questions for this? Ada soalan tak? So kalau nak tengok strain pun boleh. Tengok strain, you tengok under strain. Mana saya pun tak pasti mana pergi kat sini. Sepatutnya kena ada kat sini. Okay, never mind. So any questions? Ada tak soalan-soalan? So you boleh apply dalam project you. Siapa-siapa yang dapat project yang menggunakan shell element, you can try to model your structure lah. So before we stop our session, because our session is very short today, please ensure that you have submitted your practical test. Okay, ensure that that video is the video that is taken from hari Ahad, bukannya hari lain. Okay, please do that. It's a 30 marks, and then your project, do it accordingly. And your test number 2, the date will be announced by Puan Nurlizana. Please ask her the correct date of your test 2. Okay, is there any questions before we stop our class?
No, sir.
Yes. Ya, Muhammad Anunman. Sila tanya. Ya, Norman? Ada apa nak tanya? Okay, if there is no other question, please sign your U future. Please respond to U future macam biasa attendance. And then we will meet again next week macam biasa. Okay, that's all from me. Assalamualaikum. Ya, Muhammad Azim nak tanya apa, Azim?
Zul, kan tadi
Yep.
stress tu kan ada macam XX, lepas tu XY, YY, itu tak apa.
Itulah yang you kena faham tentang axis. That's why benda ni bukan hafal. Jangan hafal. Sekejap. Kenapa saya kata jangan hafal? Sebab saya tak nak you hafal. Bila you menghafal, you tak akan dapat faham benda tu. That's why you kena tahu pasal axis. Sekejap. Saya nak cari saya punya pen balik. Sebab ingatkan dah habis tadi. Sebab you tanya, saya kena explain lah. Sekejap. Saya dah simpan dalam pen saya. Okey, ni balik. Okey. So, bila you nak define, you have to know your axis. Axis ni amat penting. If let's say, you want to model your wall tadi dalam keadaan begini, meaning that your shear stress will be XY. Shear biasa kita buat shear XY. So when you have shear stress, so you have to find XY as your shear stress. If I want to know the bending stress, so kita punya bending will be in this. Okay, so we have to find your XX stress. Okay, so it is different kalau you buat yang begini pula. Kalau you tukar dia punya orientation jadi begini pula, katalah yang Allah. Mana saya punya ni? Okay, katalah yang ini dah tukar lah. Ini jadi Z. Ini jadi X. Ini jadi Y. Nampak ni? I'm drawing the same structure here. So to have analyze your shear adalah exact. Bukan lagi XY. Nampak tak? That's why jangan hafal. Saya takut you bertanya tu untuk hafal. Jangan hafal. So if you want to know the bending stress here, I have to find what is my ZZ stress.
Oh, okey, faham.
Faham kan? Nah, dia bergantung macam mana you lukis ni. You lukis ni axis yang macam mana. Sebab dia takkan sama bagi setiap orang. So kalau kata ada satu grup yang, dua grup buat projek yang sama, tapi kalau axis you tak sama, you tak boleh guna result dia kata, kenapa aku tak dapat sama? Sebab axis you lain. Melainkan kalau kedua-dua grup tu gunakan axis yang sama, betul lah. Bolehlah you compare, kan?
Faham.
Pemilihan tentang axis ni memang amat kritikal lah. So that's why bila buat model, you kena tentukan this axis ni. Dia punya paksi ni macam mana. Boleh
Boleh je.
Jangan hafal. Faham konsep. Tapi nak memudahkan cara, biasa saya selalu buat X dekat bawah, Y yang tegak, Z yang ke arah kita. Senang. Sebab saya selalu guna yang tu. Senang. Jadi kita pun mudah nak interpret. Tapi tak salah nak gunakan axis yang lain. Tak ada salah. Cuma you kena betul-betul faham lah. Kena faham. Okay. Ada question rather other than the punya stresses tadi? Ada tak? Okay. If there is no question, I will stop my